All right, it's my great pleasure to be here. Thank you for inviting me to this wonderful event. I want to talk about, my title of the talk is Attention to Quantum Complexity. And here I mean by attention, in one sense, I want to draw your attention to the notion of quantum complexity. But in another sense, this attention, the word attention means a particular aspect, mechanism that's used in large language models, which I am using to address some challenges arising in dealing with quantum complexity. So what do I mean by quantum complexity? What is quantum complexity? Let's start there. In order to understand where quantum complexity comes from and what it means, it is important to think about how quantum bit is different from a classical bit. So a classical bit is a switch. It has only two states, 0 or 1. Quantum bit is a little bit more like a beach ball. We call it Bloch sphere. It's like a beach ball in the sense that there aren't just the poles, but your state, the qubit state, can be anywhere in between, everywhere on the entire sphere. Now, this means, then in what sense is it still a bit? Well, it's still a bit in the sense that if you prepare the qubit in state 1 up, when you measure, your measurement repeated measurement will yield state up with 100% certainty. That's what it means for a qubit to be in state up. If you prepare in state down, you'll measure down with 100% certainty. So you can think of this bar as like a histogram. If you prepare the same state and repeat the measurement, the probability being 1 means you will always measure that state. So if there were only these two possibilities, there won't be a difference between a classical bit and quantum bit. But for a qubit, because your state, which is represented by the arrow, can be pointing anywhere on the beach ball. For instance, if it is pointing somewhere along the equator, when you measure, the measurement still has to be in the measurement basis 0 or 1, which means there is 50% probability of measuring down and 50% probability of measuring up. Of course, your state can be prepared to be somewhere in the middle. And in this case, your state is now prepared off the equator. There is a greater probability to be measured in 1. Now, already there is a richness in a single qubit, but when you go to multi-qubit, and I am making it qualified as a fault-tolerant qubit so that I don't have to think about the effect of noise for the moment. When you have multiple qubits, let's say 36 qubits, then the possible outcome of measurement for each of the qubits are going to be 2 to the 36 number of possibilities. It doesn't mean the complexity is guaranteed. If you have prepared your qubits in a state like this, everybody pointing down, once again, when you make a measurement, even though you have this many exponentially large Hilbert space full of possibilities, you will be only accessing 1 out of that many states, and that's not an effective use of the space that you have, but it's not a complex state. So how do you make a complex state that fully utilizes the exponentially large space of possibilities? Well, if you have prepared a state where each of the qubits are entangled across the entire system of, say, 36 in this case, and if they are as an entangled state, each have a probability of being measured in 0 or 1 with a different probability, now you can start to explore all 2 to the 36 possible outcomes. This is actually simulated for a particular state that we prepare for 36 qubits. So now, this is this is what we mean by complexity for a multi-qubit quantum state, that you have the weights of probability measurement outcome spread out this exponentially large space. Now, this complexity has two faces. This is a statue of a Roman god named Janus, who has two faces, facing forward and backward, future and the past. And here I want to emphasize that the complexity of highly entangled multi-qubit state, it has two faces. On one hand, it has the face that because of this enormous superposition, you have the potential to access many, many different possible states in extremely large dimensional space, which can be utilized, leveraged to solve or approach classically hard problems that suffers from the curse of large dimensionality. But at the same time, because quantum mechanics is probabilistic, each measurement will find one of these states, and one measurement will not give you the full information. In fact, when you have this many possibilities, and if your each measurement ruling of dice is probabilistic, you will need at least that many measurements to at least see one occurrence of each possibilities. That is not necessary if your state was simple. If your state was simple, every time you measure, you'll be just accessing one state. You don't need many measurements. But if you have realized through effort, through a deep circuit, realized a complex state as such, there is challenge with the readout because you need sample complexity to grow. That is, you need larger sample to understand the state. So you can make something amazing, but it can be hard to figure out what is it that you've made. So I want to talk about examples of how we can try to leverage the one face of quantum complexity and try to start approaching classically hard problems, and also how do we deal with the challenges coming with quantum complexity. So let me start first with the face of the opportunities that come with complexity. That is, trying to approach classically hard problems. Now, if you want to think about how do we find a hard problem, as yesterday's keynote speaker, Oscar Painter, have emphasized, quantum computer is not just a better classical computer. So you cannot just try to throw every problem that you wanted to solve on a classical computer and hope it will do better. We need to find, it's a tool for, like any other tool, you have to try to find what is this tool good for. So if you want to address classically hard problem with this expensive tool, try to do something that's hard, we have to first think about what we mean by a problem that we will give to a computer. The problem that we can think of giving to a computer is problem that can be solved by programming a hardware to execute an algorithm. Something that has a set of instructions. That's what computers do. Then hard is going to come when we go beyond what is doable with a classical computer. So to sort of give you to step back and think about what we mean by problem that we will give to a computer, let's look at the very first program written for any computer. This is what's called Note G, appendix of paper written by Ada Lovelace. This was published in 1843, 100 years before any real programmable machine that could carry out instruction was materialized. But she had this vision to try to program the machine Babbage had invented, which was capable in the design. There was a theory, a design, detailed design for how to build a machine mechanically can carry out operations, multiplying, subtracting, adding, dividing operations. And Babbage thought of this machine. He was trying to raise funds to build on his idea. and he couldn't get anybody to buy in with his idea. Everybody, said this is too expensive. But when she saw this machine, she thought of I don't want to just calculate. This is a machine that can carry out a sequence of operations. So if it can carry out a sequence of operations, what I want to do with this is to give a task that requires repeated sequence of operations, something that has recursion relation kind of instruction set. Then by repeating that set of instructions, I should be able to do something that is hard by hand. And what she thought of calculating was Bernoulli numbers. So here B1, B2, these are Bernoulli numbers. And she's instructing how to use memory, how to use processor to calculate Bernoulli numbers. Now it took another 100 years before actual machine was materialized. But in a sense, what we do with the classical computer today is still not far from what she envisioned. That is, we give a set of instructions that can be given through an algorithm. So then, what makes a problem hard for a classical computer? What makes a problem hard is when your simply stated rules quickly lead to exponentially large set of possibilities. Then enumerating each can become hard problem because of the time that it takes. So combinatorial explosion in possibilities lead to hard problems. Then that tells me that we can start thinking about a problem where the instruction is, again, instruction might be given in a simple recursion relation. Therefore, we would think of it as a problem to be computed, but leads to exponential complexity. And that is what we did in this paper, which is going to soon appear in Nature Communications. I had a pleasure of working with a very broad set of collaborators, very international. Each person brought different expertise. And this is something that I want to emphasize. If we want to make progress, we have to really approach it in a convergent manner. People with expertise in mathematics who have thought hard about problems that are NP hard, Sharpie hard. People who have thought about algorithms, people who know how to actually program the machine, and people who have thought about how you interface physics with mathematics. And that's what we managed to do. So I want to give you just a little flavor of how we approach this one phase of complexity that is the potential for doing something that's hard. So a specific problem that we addressed in this paper is estimating what's called chromatic polynomial. Chromatic polynomial is about enumerating number of ways to color a graph. So let's think of a simple graph. Graph is made of vertices and edges that connect the vertices. So here is a simple graph with 3 vertices. Now, if I give you 2 colors and say, please color the vertices in a proper way is defined by not letting 2 adjacent vertices to have the same color. Now, if I give you 2 color, you would immediately say, oh, I can do this way or I can do this way. So there are 2 possibilities, very easy to enumerate. You wouldn't think of that as a hard problem. But if I give you 3 colors, so here the G is the graph that I'm trying to color, and K is the number of colors that I have to work with, my palette. If I give you 3 colors, immediately the number of possibilities get larger. Now, as I increase the number of colors, the number of possibilities quickly grows. And this is actually showing the curve associated with this particular graph as I increase the number of colors. Now, if you think about actually coloring with a palette, we would think of K as an integer, but this K has been actually extended to real numbers. Now, this is a Sharpie hard problem, harder than NP hard, and it is known to be also hard to approximate. There is a very simple recursion relation. just like there is a simple recursion relation for the Bernoulli number that Ada Lovelace envisioned calculating with a computer, there is a very simple recursion relation called deletion contraction relationship that chromatic polynomial associated with this graph can be obtained by subgraphs that are made of deleting one edge that's connecting two vertices or contracting two vertices. It's a very deceivingly simple recursion relationship, but it is known that the number of possibilities grow exponentially. So how can we approach trying to evaluate or approximate this chromatic polynomial? It was known that there is a particular quantum many-body wave function which goes by the name of Fibonacci string net condensate, which is a superposition of many different connected ring configurations. So here is all these rings connected. Here are two set of ring-based configuration, and the only rule is that everything that you're working with has to be closed loop. So this again looks pretty simple. What is very non-trivial is although this state can be written graphically by hand and with a set of rules, figuring out how to implement this realization of the state was very non-trivial. And that's what we did through collaboration with IBM. And this involved using a very deep circuit. So here we're kind of showing off how deep the circuit was. It was total about 150 2-qubit gate layers to prepare this state. And we had to use everything that's available because each gate introduces noise. And we are working with imperfect physical qubits. But we were able to show that by preparing that state and then start measuring. We prepare the state, measure, prepare the state and measure. We prepare the state the same way, repeatedly and measure. And as we measure, I showed at the very beginning, if I have a truly complex state, truly anti-concentrated, that's a technical word, but state that is really spread out over the entire Hilbert space, you need that much sample, and that becomes also hard from the sampling perspective. But what's very nice about the string net condensate is that although the Hilbert space is this big, there are a set of rules that's constraining this topological state so that you only really access a fraction, but still large fraction of this entire state. Now, there shouldn't be these weights if we were operating with a fault-tolerant error-corrected qubits. There shouldn't be any weights here. These are topologically not allowed states. But you can still see from the measurement that our imperfect system was still allowing us to estimate the chromatic polynomials associated with different graphs through one state preparation. We prepare one state, and the measurement is yielding the weight associated with each of these different loop configurations, which has one-to-one correspondence with the graphs, and it amounts to evaluating chromatic polynomial for each of these graphs that are dual to this configuration, at the value that is golden ratio plus 2, 5 plus 2. And here we are showing that different topologically inequivalent configurations come with different multiplicities, and multiplicities helped gaining the fidelity. Now, for this, at this scale, it is not classically hard yet, which is why we were able to benchmark. But by the time you get to 100 qubits, that is really a scale that we cannot explicitly calculate on a classical computer. And this will be an ideal challenge, a wonderful challenge for 100 error-corrected qubits that can go into deep circuits that every major group is racing to reach. So this is an example of how we can start by thinking about a constraint-solving problem which has clear recursive relation type algorithmic definition but algorithms evaluate the possibilities, quickly explode, therefore become classically hard. Now this is kind of there's a very similar nature among all the sharply hard problems that has to do with various optimization. And I'm not saying every optimization problem can be solved, but thinking from this perspective of instead of saying, please solve this problem that I would really like to solve, but starting from the angle of what kind of problems can we define that is hard yet approachable from a quantum computer will be a very productive direction. Now I want to switch gear and address the other face, that is the face of challenges associated with readout. So why is it hard to read out or characterize a complex state? It's the challenge of large sample complexity. It becomes a hard inverse problem. All we get to know are the measurement outcomes. And each measurement outcome adds just a notch to that full distribution. So from that limited amount of information that quantum mechanics afford us to access, we need to figure out what the nature of the state is. And fundamentally, it is not possible to reconstruct or understand the full nature of the state, but what we really care is often some aspect of the nature of the state. So now it becomes the question of, instead of wanting to know it all, because that's not practical, deciding what can I figure out that is achievable, affordable, yet meaningful and productive. So this is where I would bring in using AI tools. So if I have this kind of complex probability distribution in large space, and if I'm trying to figure out what I have just from a limited sample, then a tool or strategy that is developed to approximate a large probability distribution to the extent that is practically useful can be very helpful. And what is such a tool? There are tools that are developed especially for large language models. So here I want to highlight our recent work on quantum attention network. Here, this is the inspiration for the title. Here, attention means attention mechanism, which is used, which really revolutionized the language models in 2017. And you can find more about this work in this paper. Once again, this was a large collaboration, and I benefited greatly through my collaborations with my colleague at computer science, Kilian Weinberger, and his group. It's been a very productive mutual learning experience going across the domain boundaries. So this is our architecture. Now, this image is not very informative, although I'm showing you, my experimentalist colleagues like to show their refrigerators, which has a superconducting qubit chip somewhere in the middle, and it gives the audience or viewer a sense of there is something concrete. So this is kind of like the refrigerator. You look at the refrigerator, it doesn't tell you much about how the qubits are working. You look at this thing, it may not tell you much about how this is working, but this is our sort of the machine learning architecture. So it's taking all these shots, the measurement outcomes in batches, and something that we cared a lot learned to care a lot through experience is to think from the data perspective. What is the structure of data, and what is special about my data? What kind of symmetry my data has? Although we productively use the attention mechanism, we had to be very careful with the difference in the data structure between language and these snapshots. Language is naturally a sequence. There is an arrow of time. If I say a sentence, the order in which I said the words matter. Now here, if I treat my snapshots like a word in a sentence, these shots were taken randomly. they occur randomly and there is no meaning to the order. So when we give data to machine learning algorithm, it's really important to avoid trying to learn artificial structure, non-existent structure, because a lot of research can be wasted there. So we struggled with this problem for a long time, and eventually we figured out we need to get this symmetry right. So the algorithm that we used was designed to be permutation symmetric. At the end, we will give lots of shots, and we will try to figure out how one state is different from another state. A classification task, which is the simplest task we can ask. So I presented this as a very challenging problem, and we have to frame this really hard problem into something that is doable. And the easiest thing that you can do with the least sample greedy thing that you can do with machine learning algorithms is classification. So what we were able to do with this quantum attention network is distinguishing data from state that is volume law entangled and area law entangled, state that is topological and trivial, state that is taken from a very deep circuit, therefore very, very complex, and state that is taken from a shallow circuit that is less complex. And in all of this, what really was important is taking this is the full distribution, that if you had the full knowledge of the state, you would know this, but that's not what we can access. We access limited set of measurement, and trying to figure out from this limited amount of measurement, what is it that we have was the major challenge. And in doing this, the attention mechanism was used to learn the shape of the distribution, the moments of the distribution. Now, most of us, having taken introductory statistical mechanics, think about when we think of data, the first thing we think of is average, mean, maybe median and mode, and then standard deviation. That's sort of, as far as non-specialists would go. But standard deviation by itself, which tells you the width of the distribution, does not tell you the full shape of the distribution. So here, the way we are approaching this problem of complexity, complex state, is to think that, well, we want to learn from this limited data, rough sense of the shape of the distribution. If there is a difference between shape of the distribution between this limited measurement and this limited measurement, using the attention mechanism, which can learn high-order correlations when we stack up the attention mechanism, would allow us to distinguish between different states. So here, I will just show you just a little bit more inner workings of what we did with complexity growth and random circuit sampling problem. This problem became sort of face of quantum simulation through the highly publicized set of works from Google, where they declared quantum supremacy. And the claim was to achieve a very complex state that you would get to by going very deep, building a deep circuit, is so complex that it is hard to, it will take a long time to classically simulate it. Now, there has been a lot of debate about this work and whether it is, or in what sense it is, or if it is at all, a demonstration of quantum supremacy is not that's not the point of my interest. What I was mostly interested in was the fact that in this original set of work, the way they were able to tell that they have achieved a complex state was through comparison between the distribution of their data from the quantum hardware and classically simulated data. And we wanted to take classical simulation out of it, because if you want to go to problems that cannot be classically simulated, you cannot be benchmarking against classical simulation. So we wanted an approach that can really tell the difference between a shallow circuit state that is less complex and a deep circuit state that is more complex by just looking at the data, just from the data from those two sides. And in our paper, we showed that this is possible with the strategic leveraging of the attention mechanism. And the way it works is that the attention mechanism essentially takes the input data and it's calculating so-called attention score, which amounts to looking at second-order correlation in the rotated basis of the data itself. So it builds one layer of self-attention builds in second-order correlation or second moment. But by stacking up this attention mechanism, we were able to build very high orders of correlation. And we showed that in order to learn the difference between very deep circuit and somewhat deep circuit, up to the point where they become not distinguishable anymore, required going up to 40th moments of the distribution based on how many layers that we needed. But what we showed here is that looking at this problem that complex states present us from a data-centric perspective and looking for a suitable tool for that data problem, paying a lot of attention to the structure of the data problem is a very productive and perhaps the only way we can go forward. Another important data problem that arises in dealing with quantum simulator states is decoding. Now, this decoding is decoding in the sense of decoding fault-tolerant qubits and circuits. And this was work done in collaboration with my student, Yi-Ching Zhou, and Killian's group again. So what does it mean to decode a quantum error correction code? So quantum error correction code, which Oscar also briefly alluded to yesterday, is the idea that you want to build robustness, tolerance against faultiness of individual qubits through introducing redundancy. So you want to use multiple qubits, in this case, I think this is 1, 2, 3, 3 by 3, 9 qubits to represent one logical bit of information. If you make the number of qubits that you use to represent one logical bit of information, the larger you make the redundancy, the more robust it should be, if it is working. And that size of redundancy is called code distance. But introducing redundancy for qubits is harder than with classical bits. Classical bits, you can just copy and multiply and repeat them and have them all represent one bit of information together. But with qubits, because you cannot clone a qubit, you need a clever approach. Those are called codes, error correction codes. So if you have one logical bit of information represented by these many qubits, and now what you do is you observe some information that you can extract from that system without destroying the system. That's called syndrome measurement. So you extract syndrome measurement, you keep observing and observing and observing. You're watching to see as individual qubits states change and fluctuate, you're watching to see whether the redundant information, that logical information, got contaminated. So you watch the syndromes as a time sequence, which are affected by noise, and you want to know, has my logical bit of information been contaminated? And when it is discerned to be contaminated, you will go in and fix that. That's the error correction. And having a large error correction code, a robust error correction code is meant to bring in more robustness and fault tolerance. It doesn't mean the error will never occur. And having the error correction code means that you can detect that error. And this detecting is called decoding. The problem is from the measurement outcomes that these are syndromes, to decide whether the logical error occurred is a difficult inverse problem. And the conventional approach is to choose a noise model and forward model, simulate out what are all different ways the logical error or non-error situation would materialize. And then you look at the syndrome sequence measurement and try to guess whether the logical error occurred or not. And this is using graph-based algorithms. So what we did, the ML approach would be, instead of trying to solve that reverse problem by forward modeling and fitting, what you want to do is to take a lot of data and use a syndrome measurement to train the model so that the model will learn from diverse experiences with the syndrome measurement when the logical error error looks like and when non-error looks like. And this paper by Google have demonstrated that machine learning-based decoder has a virtue. It's much more effective compared to the conventional approaches. But these efforts thus far have mostly focused on memory aspect, whether trying to decide whether error occurred on the memory of the logical qubit. However, recently, it has become possible to implement gate operations between logical qubits. And that's the logical circuit. Now we are entering the era where we can actually operate logical circuits. But decoding logical circuits are a much harder problem because now you have two set of systems between which the gate operation would propagate and correlate error. So we approached this logical circuit decoding problem once again thinking about the structure of the data. Structure of the data is that we get syndrome measurements, and syndrome measurements are coming in as a time sequence. So we want to approach this problem with an algorithm that is designed for time sequences. And now language is really a very close analogy. Another thing that we wanted to do was to build a decoder that is versatile. If you want to make a different circuit, you shouldn't need to build a new decoder each time. All the circuits are built with a set of fixed gate elements. So what we decided to do was to designate a decoder, what's called core, in the long short-term memory. It is a language model algorithm, but sort of a unit, a core, associated with each of the gate elements. And this way, we can treat a 2-qubit gate just like all the single qubit gates by having slightly larger core, which will be taking 2 inflow of sequence syndrome measurement. And with this approach, we have shown that indeed our logical accuracy that we can decode goes up, going from code distance 3 to code distance 5. That is, when you increase the redundancy, our accuracy went up. What most importantly, the wall time, the time it takes to decode with our decoder compared to the conventional manual approaches is scaling much, much nicer. In particular, if you look at here, code distance 5, our MCCD multi-core circuit decoder shows essentially no change in the decoding time as we increase the circuit depth. I said earlier to evaluate or estimate chromatic polynomial, one needs about depth 150 logical circuit depth. If you're doing 150 circuit, deep circuit, you really don't want your wall time to be growing like this. And what we were able to show is that our modular approach with the machine learning algorithm is showing a great advantage in terms of the wall time. So now I want to step back a little bit and talk about where there are opportunities to seek synergy between AI and quantum. We talk about AI for quantum, that is using data-centric AI tools to solve pain points, bottleneck problems that arises as we try to make progress and do meaningful things with quantum computers. And we also talk about quantum for AI, that is what can quantum simulators contribute in solving problems that are currently thought to be or solved by AI. So in the AI for quantum direction, I've talked about decoding, which is a case of state characterization. I demonstrated how you can build an efficient decoder for error correction. And the key is to recognize data, in this case, is a time sequence. And the decoding problem is a classification problem. You just have to make a binary decision. Did the logical error occur or not? There are only two choices. And that should be doable with limited amount of data. The key to the target, the figure of merit will be scale. How large a system can you decode? How quickly can you decode? And how versatile is your decoder? There's another place where the sort of domain that I haven't touched, but there is a increasing need for control and compilation. As you make larger and larger system, control and compilation becomes a challenging problem. And now the data can take the form of graph as you try to map the circuits that I can draw on a piece of paper to a physical device with all its constraints and connectivities. That also becomes a complicated, challenging optimization problem, and I believe there are opportunities there. Now, what you can use quantum for AI is you want to use the quantum mechanics, which governs dynamics, to actually simulate a dynamical system, which is necessary to learn spectroscopy. And you might also want to approach optimizing constrained optimization problems. These are hard things to achieve until you have really reliable hardware in some sense. And so that they're, in a way, somewhat farther out. But I think we're starting to make progress and starting to approach the hardware that can start to show at some level of proof of principle and start to build up towards a real application. So in my talk so far, I talked about two phases that is the phases of quantum complexity. There is a phase of that you can simultaneously, in principle, have access to large dimension of Hilbert space, means you can aim to solve classically hard problems. There is the opposite phase of challenge. The fact that you have a complex problem comes with sample complexity issues. Here, for solving classically hard problems, I showcased an example which we believe is a new direction to try to target advantage. And this is a case of chromatic polynomials. Now, a particular state that we figured out how to implement in this paper is not evaluating chromatic polynomial for all numbers of colors. It is for a special case of golden ratio +2. However, I believe demonstrating a win in one problem is going to open the floodgate for us to start finding other places where you can make a big difference. And our estimate is that what you really need is about 100 fault-tolerant qubits, 150 deep circuit, and we would love to try to implement this. And on the other opposite phase of challenges associated with the large complex state and the fundamental laws of quantum mechanics that we can only know through measurement in a probabilistic way, I advocated for using data-centric AI tools. Now, stepping further back, the title of this conference is aiming at going from 100-year history of quantum mechanics to industrial applications. Now, I want to propose what I believe is truly necessary for us to change the industry or change the human history. It requires convergence between different domains. Quantum mechanics was discovered by physicists. Physicists figured out quantum mechanics as physicists struggled, puzzled over various observations that they couldn't make sense out of. Observations of radiation, observations of what we could figure out about structure of nucleus. It was clear that the rules that govern nucleus and the electrons and the spectroscopy was not something of classical mechanics. Therefore, many people who are in the field come from physics background, who have taken several years of quantum mechanics courses. Another important contribution physics brings is that of material science. Material science that's been perfected while we were going from the initial understanding of semiconductor that started from intellectual curiosity to transistor and to integrated chips. Physicists, condensed matter physicists, material scientists have really studied materials, and we've learned how to optimize materials. Also, optics is extremely important. That's what you need to network. That's what you need to communicate. And there are every quantum computing platform involves optics in some way. Microwave is also electromagnetic wave. And cryogenics for superconducting qubits. So clearly, physics has a big role to play. However, if you want to go from having a refrigerator holding chip to doing something useful, solving a problem, we need to think of something to program, like Ada Lovelace thought of what to program. We need to think of the problem to program. We need to think of what are the good problems that we can program on this new hardware. It involves working with many components. It involves challenging optimization just to realize quantum computer. So expertise from systems engineering, control, compiling, electrical engineering, this domain has to come in. Information science, mathematicians, and people who've been thinking about algorithms also have to come to the party. And now I'm advocating the AI tools that's been developed for real-world data problems can have a large role to play, even before thinking about what problem can quantum computers solve better than the given available AI, but in bringing value and function out of near-term hardware. Now, this is actually very hard. It's easy to say that we need to have interdisciplinary collaboration and convergence, but it is very hard because everyone, researchers in each domain, come with their familiar set of convention, their familiar set of vocabulary. So in order for a convergent solution to be achieved, what we really need is curiosity and humble mindset, being curious about what's there to learn, and willing to ask us what might be a stupid question. Willing to preface, well, I'm new to this might be a stupid question, but I'm curious about this. So I hope that this conference will bring a lot of people from different backgrounds together, and we start to find new solutions and start to brainstorm together. With that, thank you for your attention.